Our next speaker is Desi Ivanova from Oxford.
Thank you. So first of all, thank you for inviting me to this wonderful program and this great workshop. This is a new slide deck, so if anything isn't clear, please interrupt me and ask questions as I go along. I'll try to stick to the 30 minutes and see how far we go. Right, so I'll be talking about uncertainty quantification and sort of calibration of large language models. And here's the quick agenda. So we'll kind of briefly see what some people describe as a reliability capability gap in these models, and sort of briefly discuss why this is relevant to AI for science, given this is the theme of this workshop. And then I will argue that uncertainty can help us address some of these reliability issues. We'll go through a quick overview of some uncertainty quantification methods for language models. And then I'll talk about a recent paper, semantic level confidence calibration of language models, which is joint work with a wonderful PhD student at Oxford, Tom, and also Phil Torr and Tim Rudnam. Okay, so I shouldn't probably convince anyone that LLMs are being deployed in quite high-stakes domains these days, right? So we're seeing applications in fields like education, in healthcare. There's some attempt to automating science as well with these models. And the big problem, obviously, is that current language models are extremely unreliable. And as I said, there exists this capability reliability gap that makes them not particularly useful to be deployed at such large scale in practice. We know that they hallucinate. They're very sensitive to small perturbations to the prompts. They tend to be overconfident. And they are still getting very, very simple questions wrong. And I tried this 2 hours ago. The classic question asking a model which one is bigger, 9.11 or 9.9. And this is Claude Sonnet 4, so state-of-the-art model of Anthropic. It is still getting it wrong. So it's still claiming that 9.11 is greater than 9.9. Okay. But back to some kind of more practical things, right? So Sakana is a company that claims to be automating science, and here by automating science, they really mean writing machine learning papers automatically, and you would say, we have more than enough, supposedly human-written papers in machine learning already, so why are we doing this exercise? That's a separate question. But what it turns out is that this is a Nature article that discovered that some of these LLM-generated papers are actually plagiarized from existing, works. And one of the authors whose paper was plagiarized, in fact, commented, looked at the generated paper, and indeed said, well, obviously they're introducing an existing method, so that's clearly plagiarism that is being claimed as novel. And as a response, the company generating these papers was pretty defensive, saying, oh, that is absolutely false, and these claims should be ignored. So there is a bit of a problem there. Then LLMs are said to will be substituting, university lecturers and school teachers and so on. And indeed, OpenAI recently released their GPT-5 model that is claimed to have PhD-level capabilities and knowledge, and that it hallucinates far less. And if you were careful, like some people, you would have found out that in their live demo, when they released the model, they actually described the, how plane wings generate lift, described the incorrect theory, right? So you would hope that a PhD student in kind of aerospace engineering would know such things and wouldn't be, spreading misinformation almost. And finally, and kind of most importantly, in my opinion, simply because LLMs are said to be extremely good at code. And certain CEOs have claimed that in 3 to 6 months, and that was 6 months ago, so now AI will be writing 90% of the code. And that might be true, but if it is, we're in big trouble. And the reason for that is that the percentage of time that these models get the tasks done to completion is actually extremely low. And these are some results from a company called Meter that looked at, from pretty old school models now up to GPT-5, released, a few weeks back, looked at various sort of software engineering tasks and how long they take, right? So on the y-axis we have, tasks that take 4 seconds up to 1 hour. This is log scale, right? 4 seconds up to 1 hour, and this is the success rate at 50%, right? So, for example, GPT-5 can successfully complete 50% of the tasks that take just over an hour, or several hours actually, right? And if you look at tasks where reliability is at 80%, you can only do tasks that are just over 6 minutes long, right? So if we are using these tools to automate the jobs of software engineers, we can comfortably say that a lot of the code doesn't work as intended, right? So what can we do about it? As I said, I think one way to at least start to address this reliability capability gap is through good uncertainty quantification. I don't necessarily think UQ can solve all of these problems on its own, but it can at least help us track and escalate potential reliability issues, right? So for instance, as it was discussed yesterday in the first keynote, it will be great if the user can see on their screen responses alongside confidence flags, right? So low confidence statements being kind of marked in red and high confidence being marked in green, for instance. And hopefully we can start to build systems where they are taking uncertainty quantification into account, and either the model is abstaining from answering your query, or sort of it gets delegated to kind of a more capable agent. It could be another model, or it could be a human, or invoking a tool, or whatever it might be. And obviously, for all of this to kind of work well, we need confidence measures that are well calibrated, right? So if we're going to delegate the bottom 10% of queries to a human being, we better be sure that it is the bottom, right? The bottom 10% would have a low probability of being answered correctly by the model. Okay, so I will just briefly go through a few methods of eliciting confidence from language models. This is really, really not exhaustive. The landscape and the taxonomy of methods for doing this has grown, exponentially in the last few years. So here I'll focus on the following 3 main approaches, which you can then mix and match, right? So the first one is what is called self-reported or verbalized confidence, which literally just means ask the model to report its confidence in natural language. And here is a quick example. You can ask the model who directed The Wolf of Wall Street, answer and report your confidence from 0 to 100%. And the model will return an answer and a confidence. Here on the right, I'm listing relevant references if you would like to kind of look into these. Then we have something called consistency-based models. And for these, we kind of have to sample from the model or generate multiple responses from the model and look at frequencies, for example. We can also look at other things, but kind of the simplest one is to look at frequencies. And for example, the model can, out of 100 queries, well, after asking the model the same thing 100 times, it may return 95 Martin Scorsese and 5 David Fincher, and from here we can say the model is 95% confident in its answer. And finally, we have methods that are sort of based on internal model probabilities. And here a good example is what we call p-true. And what p-true is, you ask the model to sort of affirm or deny a statement, right? So going back to our example, you can say the following: Scorsese directed The Wolf of Wall Street, true or false? And actually, you don't even have to wait for the response from the model, right? You can just look at the probability of the next token being generated being true, conditional on this statement, and what this probability is. Okay. And as I said, you can kind of mix and match all of these things. Now, a lot of work has focused on this consistency-based approach, and this is sort of the paper that I'll be discussing, where we're sampling multiple times from the model, and if all of the answers kind of come in this form, that would be great. But oftentimes, the model produces slight variations of the same response, right? So, for instance, 95 of the answers might be Martin Scorsese, and 5 of them could be Scorsese directed it, right? So this will still count as, the same answer. So basically, to kind of solve this problem of, actually counting semantically equivalent responses as correct as well, people have started looking into semantic level approaches to quantifying uncertainty. And this is how it goes, okay? So we're going to start with our query again. Sorry, I'm changing the query, but it's the same process. So we start with a query. We're going to generate multiple responses, okay? And we're going to group them into semantically equivalent clusters. Now, the way that this is normally done is with something called natural language inference model, which is kind of a relatively lightweight BERT-based model, and we're testing for sort of bidirectional entailment. Is this response contained in the second one, and vice versa, right? Now, having worked on this project, I can say that this is really not trivial. There are a lot of edge cases, and you kind of have to be really careful how you how you both construct the queries and how different things like numbers and dates are handled. And if you're not careful with that, kind of things don't really work out. Okay, so what do we do afterwards? Once we have these semantically equivalent clusters, we can define semantic level confidence metrics. And there's lots of ways, right? You can. These are the only seven that we looked at in the paper. 2 of which kind of exist in the literature as well, and 5 others that are kind of variations of the first 2, but haven't been sort of discussed in the past. So let me just briefly kind of say what these are. As an example, this is kind of an empirical semantic consistency measure where we're just looking at, how, which is just proportional to the cluster size, right? So if you have a cluster with lots of responses, that means that you should be more confident in that response. And if you have clusters with only 1 or 2 responses, this is sort of less confident. Then you could look at, so this S score is simply the length normalized log likelihood of your response, and you can do various variations of it, right? So you can take the mean. We also consider something that we call a Bayesian-inspired semantic confidence score, where we're using the empirical here as a prior, and we're kind of looking at this term as a likelihood. This is tempered version of it. We're looking at something that looks into internal consistency of these clusters, and we're also looking at something that kind of forms a Gibbs posterior as well. It's not really important what these metrics essentially are. The point is you can construct many of them, and at the end of the day, which one should you use? Like, that's one of the questions that we are looking to answer. And also, are they really different? Oops. Oh, there we go. Okay. Are there any questions so far? Yes.
How do you cluster the Ys? I did not get it.
Right. So we're using a separate model. It's normally a BERT-based natural inference model, which can tell whether a statement contradicts another statement or a statement is contained in another statement, right? And
so to take the composers, for instance.
Yeah. Right. So you do pairwise comparison. You check, is this response contained in this one? No, it's not. And then you check, is this response contained in this one? And it isn't. And when you look at this response, is it contained in this one? It is contained in this one, and vice versa. Is this response contained in this one? It's not quite, but almost it is, right? So the model would cluster these two together because they're semantically the same, and the others will have their own cluster. Yeah, so that is a separate model. You could as well use another or the same LLM, right, to just ask you to, can you please cluster these for me? And that also has been used in the past. Yeah.
Thank you.
Yeah.
So the pre-LLM semantic indexing was done with dictionaries, right?
Okay.
Or like we still use an LLM, or I'm assuming that you use BERT to get the embeddings to do the classification.
So these are fine-tunes of BERT.
Yeah.
Yeah. So they're fine-tuned on natural language inference tasks, and they're used just for natural language inference. Yeah. So for these semantic relations between statements.
Yeah. Thanks.
Yeah. Okay. And these are good questions. I think that is like the big question mark about all of these semantic clustering style. What's going on? Sorry. About these semantic clustering style approaches is that the clustering really isn't very a particularly trivial task. Okay. A quick note. So only the first approach, where we're just looking at the empirical sizes, effectively, of the clusters and using that as a semantic confidence score, is applicable to black box models, right? So, for instance, models like OpenAI and so on that are behind an API. For all of the others, we're going to need access to the model itself so that we can actually compute all of the log probabilities that enter these calculations. So yeah, we refer to this as a kind of a black box method, and these are kind of white box, right? You need access to the models. Okay, so we talked about elicitation. Now, how about calibration? So far, most prior works have looked at token level calibration. And this works great if you consider tasks such as multiple choice question answering. And because we train language models with log likelihood loss, which is a proper scoring rule, and we also do it for one epoch, that actually keeps the model pretty well calibrated on a token level. And there is lots of evidence for that, right? So this is from the GPT-4 technical report, and the data on which this calibration plot was constructed is MMLU, which indeed is a multiple choice question answering data. So we see very good calibration, right? The problem is that post-training, which we do with RL, which is not the proper score, like the losses there are not proper scoring rules, actually destroys calibration, and this is also very well documented, right? So this is the same data set, and we see, things going wrong much more. But the good news is we can perform simple temperature scaling, and I'll explain what it is in a second, to sort of get back to well-calibrated probabilities. Okay, and this is from an Anthropic paper from ages ago now, 2023. Okay, so who knows what temperature scaling is, just so that I'm aware of, yeah, okay. So temperature scaling, in the context, of language models, temperature is this parameter that controls the randomness in the generation, and by extension also controls how diverse our outputs are going to be. And if we denote by p phi of x, conditional on x, where x is our input prompt, right? So the question. This is our autoregressive model. At decoding time, right? So when we're generating, the model will sample the next token from this scaled softmax distribution, right? So zt is our logits at time t, and tau is this temperature parameter. And when we set the temperature to 0, or very close to 0, what we're getting is essentially greedy decoding, right? So this converges to the argmax at tau equals 0, and it is deterministic up to any non-determinism in the GPU itself. If you do temperature 1, this is kind of the standard softmax. So you're just sampling from the categorical distribution, and if temperature is above 1, you're sort of flattening out the distribution and you're producing more diverse tokens. Andrew yesterday asked, why are we not optimizing things more granularly, right? So can we not do like per token temperature scaling? And indeed, there are some works that have looked at per token temperature scaling, and we do in our work as well, right? So instead of having a fixed scalar parameter tau, we can actually define a token-specific temperature by training a separate little component that basically takes your hidden representation and outputs a temperature parameter for each token in your sequence. Okay, so we'll also look at that. So you get different taus for different tokens. And what we also consider is kind of a more classic approach to calibration, which is flat scaling. Flat scaling simply learns the sigmoid to convert the classifier's original scores to calibrated probabilities. And because the number of classes in LLMs is super large, right? So it's on the order of thousands. We are only learning diagonal parameter as opposed to the full matrix, right? To make it kind of more manageable. In what follows, we'll be denoting the temperature parameters by theta, and depending on which approach we take, these are slightly different things. So either this is the other way around. For the temperature head, we have this psi parameter, the tau scalar for temperature scaling, and WMB for the flat scaling. How are we going to optimize the model now? Right, so we consider two different losses. Simple standard negative log likelihood, which kind of you can think of as continued pre-training, although the model has already been kind of post-trained. But yeah, we just have negative log likelihood on our training data. And we also consider what is called the selective smoothing loss, which was introduced in this paper here last year, which essentially looks to minimize negative log likelihood for the correct tokens and maximize entropy of the distribution for the incorrect tokens. And we have the usual empirical training objective, sampling from our training data set. Okay. Now, I'm going to show you results, right? So this is very empirical work, as most works in LLMs. So I'll start with one of these charts, and then I'll show you all the others. So we have three different data sets. trivia QA and natural questions, which are what we call closed book data sets. Namely, kind of the model is supposed to the model is supposed to. We're testing the world knowledge of the model. And we also consider this open book dataset, which is essentially an extractive question answering problem. You have some context, and you're supposed to answer questions on that context. And what we can see in here for the llama model is that this is the calibration on the x-axis, and we have ability to discriminate correct from incorrect answers on the y-axis, so our ROC. And we see that our base model has very poor calibration. So the blue items here is our base. And we see that any sort of temperature optimization or other sort of calibration methods actually improve both the calibration and the discrimination ability of our models. And indeed, this holds for all data set for this model. And indeed, it holds for all of the other models that we consider in this case. Now, we are improving calibration, right? So points are moving to the left, but we're also improving discrimination ability of the model, right? So kind of points are also moving upwards. And that shouldn't necessarily be the case, because there is no reason why doing something about uncertainty should improve the accuracy of your model, right? But basically what happens is that because we're generating more diverse responses, we tend to reduce the overconfident, the errors in the overconfident responses, and kind of spread the mass over clusters, which also kind of tends to improve discriminative abilities of these models. And here is a sort of a quick example how, and that's from an actual data set, right? So a model gets something wrong, but once you temperature scale, you generate more diverse responses, and eventually it gets the correct answer. Here is a quick plot that if we do selective accuracy, so we're declining to answer a proportion of queries, that generally speaking, we are improving accuracy as well. So that's something that you would hope that a good uncertainty metric actually achieves. Results are a little bit mixed, right? So, temperature scaling does a bit worse than some of the others, but in general, doing calibration and rejecting, uncertain responses is improving accuracy. And these are all the results that I wanted to show you. And we have 1 minute to sort of maybe think about some of the open problems, which in my opinion is basically everything. So first of all, none of the confidence measures checks for factuality. And kind of a question that I have for myself, and I guess for everyone really, is can we even talk about factuality in purely generative tasks, right? We have no idea what the models have been trained on. Why should we expect them to have factually correct knowledge? So should we just stick to retrieval tasks and talk about factuality there? Or can we say anything about factuality errors in general? Second, we don't have good benchmarks for assessing uncertainty and reliability in language models. And in fact, we don't have good benchmarks for assessing their capability either. So just benchmarks are a bit problematic. And kind of going back to some of the discussion yesterday about utilities, should we take utility into account when we're making reject or delegate the question to a human? And how can we do that for every human individually? I don't exactly know how I feel about utility theory these days, but yeah, I'm happy to hear what the audience thinks. So yeah, I'll stop here and see if there are any questions.
So in the interest of time, we can take one question and then continue during the break.
In fact, it's more remarks. So thank you for the great talk. It's an important topic. Just wanted to point out the work of Fabian Suchanek, with someone coming from automatic reasoning, who is trying to assess the factuality of LLM answer, leveraging reasoning and database where facts are checked.
Yeah, I think that's exactly right. Like you need a separate database you can refer to.
So maybe that's
yeah, for sure. I'll follow up.
Okay.
Thank you.
Thank you.